Good morning, everyone, and welcome to MarRI-UK's webinar on laser shearography and its application to marine structures. As Alder said, my name's John Hudson, and I will chair today's session. Laser shearography is a very promising new approach to non-destructive examination of materials and structures, especially composites. It can be used in the assessment of new structures, the through-life inspection of structures, and also to examine and approve structural repairs following damage. We're fortunate to have two very knowledgeable speakers this morning. Firstly, Emeritus Professor John Tyrer from Loughborough University, who will give us an overview of laser shearography and its applications to the non-destructive examination of composite structures. John specialises in the development of innovative and bespoke laser-based imaging technologies. John will be followed by Peter Amin, Senior NDA Specialist from Lloyd's Register. Peter will give us an update on how laser shearography can be used to gain class approval of marine structures in the build, support, and to validate structural repairs. The authors are both very knowledgeable about their subjects and happy to tailor their presentations to the audience's level of understanding of the technology, either basic or expert. As a consequence, all is going to issue a poll, which if you could complete, the presenters will use to steer their presentation a little bit. Each presentation will present for about 15 to 20 minutes. If you could use the Q&A session, the Q&A facility. If there are any burning questions after each presentation, we'll ask them then, and then we'll have a more open session at the end of when both presenters have completed their presentations. And you can either ask questions using the Q&A facility, or you can raise your hand and I will facilitate you asking the questions directly. We will close this session at 11 o'clock. So on that basis, John, could I ask you to start the first presentation? Thank you.
Yep. Okay. Right. If I share my screen. So I'll just share. There we go. I hope everyone can see that. Yes, my name is John Tyrer. This is co-hosted with Simon Dickinson. Yes, I'm from Loughborough University. We set up a spin-out company 30 years ago, Laser Optical Engineering, and we manufacture the instruments. The technology was invented at Loughborough, and we provide service capability. We maintain the entire RNLI fleet, have done for over 25 years, as well as for lots of other people in maritime, aerospace, automotive, etc. So in terms of what we're looking for is an ability to do quantified inspection, typically using a single individual. And you can see there Andy using one of our instruments. This is a vacuum hood, and it looks at an area of the vessel, and it takes a few seconds to do that inspection. What it allows us to do is to see inside the structure and the way the defect is influencing the performance. So this is a very different form of non-destructive testing. We refer to this as an active non-destructive testing technique, because what we're actually doing is putting the target under some very light influence of work, the typical work it's going to see. And then what it does is it reveals, because it produces fringe patterns, and you can see those here, fringe patterns that are a function of the mechanical strain on the subject area. And if there is any weakness or problem in that area, the strain energy that is being generated on the structure has to flow around the weakness. And what this does is it gives us a highlighting feature. We can actually identify the size, shape, orientation, etc. of the defect, but we can also determine its significance. So if it's just a minor defect that's not really malignant, then we can log that and maybe look at it after the next mission or the next trip or whatever, or we can plan a repair strategy, or we can condemn it there and then. So here, just for a bit of fun, on one hull we found a trapped glove that the individual had got these gloves on when he was doing the manual layup, and obviously put them in his pockets of his overall while he got out. And one of them fell out, and subsequently the next day, the glove got bonded into the structure, and we were able to see it. So I mentioned the RNLI. We look after all of the vessels, the inshore fleet as well as the offshore fleet. Here we can see at a refit, we can see here a fringe pattern that's being generated. You can see that sort of frying pan shape. And what we do, Andy then generally chalks up on the structure. And lo and behold, when that was cut in by the repair people, you can see there was a debond problem. The equipment is all inherently safe. It's quite lightweight, so it allows single person operation, whether male or female. And we're looking at being able to scan about a square meter per minute, typically. The reason that this has sort of come to the fore is, if you remember the Cheeky Rafiki, which was a chartered yacht that was on charter coming back. So it's a British flag charter. She had a British crew in. There's the 4 individuals. And they complained as she was coming back from, I think it was the Caribbean. She'd come up via the east coast of the States. And she was about 900 miles off Boston. And they'd reported creaking and groaning noises that weren't good. They were told to just get on. And anyway, in a storm, the keel snapped off. The boat turned turtle straight away, and the 4 crew were thrown out. MABE, the Maritime Accident Investigation Board, did a very thorough analysis. And in yellow here, I've just highlighted, she'd grounded earlier in her life, and the keel had been damaged. The joining had been damaged. And there was various debate amongst surveyors, etc., and repair people. And so MABE's analysis was there is a need for regular structural inspection by nominated competent persons as part of a formal verifiable procedure. They wanted to see a best practice industry-wide guidance developed, and inspection for damage should be undertaken by suitable competent persons. They went on to mention there should be proper training courses that could provide these people, and there should be agreed ways of doing that. So we set off with, following on from the MABE report, to generate the requirements that they set out. We approached the British Institute of Non-Destructive Testing for the development of a marine composite NDT inspection program. We held our first meetings in 2018, and the objective was to produce a proper training and certification scheme, and that should enable manufacturers, owners, insurers, and operators of composite vessels to either identify or to have identified and employ competent and qualified inspectors. I'll just give you a quick summary of what we've done. We, as a community, got together via various meetings within the NDT community under the auspices of BINDT, and 2 inspection methods were highlighted as probably the more relevant. That doesn't exclude others, but it simply said these 2, and we got started. However, COVID got in the way, and it slowed down everything. We split the committee into 3 groups. One, headed by Holly Phillips, was in the product technology area. Ultrasonics was headed up by Chris Phillips, and Shearography by myself with Chris Minton. To date, we've now got a syllabus together that was submitted in early 24, and the team at Bint, Patrick Bolton, etc., were making sure we did it all correctly. We're doing it that we are looking for certification schemes that will give things the qualifications and competency to the operators. This is not just buy an instrument and go and use it. This is a proper, let's have a look at how it's done. We've now identified a couple of level 3s, and we've now produced the exams for level 1 and level 2s, and the samples are now being manufactured. So it's hoped we will start to get the courses out in 26. You'll hear subsequently from Peter from Lloyd's Register, but we've now got shearography added as a approved technique for inspection. So what is this speckle stuff? If you've ever illuminated a surface with a laser, the surface compared to the wavelength of light is usually quite rough, and it generates a pattern, a speckle pattern, and it just looks like the carpet. You know, it's just a granular pattern of dots. And what we do is we store a picture of the object in its unloaded condition, and then we subtract the pattern that is generated when we put the object under load. Now, the point is, it's non-destructive, it's non-contact, we're illuminating from a distance. It's very sensitive because it's based around the wavelength of light, and it allows us to see the full field. So what this does is it allows, when you subtract those, you get a fringe pattern, which we are able to measure. Those fringes are isocontours, they're contours of strain. And by changing the amount of shear, we can vary the strain gradient that each fringe represents. So just to bore you with some descriptions, I'm a simple mechanical engineer, and I like to work in Cartesian space. So the screen that you're looking at, horizontal movement across the screen, we refer to as horizontal in-plane strain. Vertical movement within the screen is vertical in-plane. And if you push your screen with your finger and bend it front to back, that is the out-of-plane component. And if you add those three components together, you can get the overall strain field. Just to try and put some distance and, you know, create the illusion of academia here, I've put in an equation. One of the important aspects is the axis at which the instrument looks at the target and the axis at which you illuminate the surface. The bisector between those two is where the sensitivity vector is. That's where the instrument is sensitive to. And if you remember your school science, we can resolve those so we can get a horizontal component and we can get an out-of-plane component. So what that means is if we bring that illumination beam on axis to the observation beam, in other words, theta here drops to 0, well, then we are able to measure just pure out-of-plane motion, which is good for delamination. But if you want to measure the things that influence composites, which is fiber breakage, adhesion, etc., then you need to be measuring the in-plane component, because the out-of-plane component will be insensitive. So by varying this angle, we can change the relative sensitivity. So by having this off axis, we can get a combination of both the in-plane and the out-of-plane components. And just to make the point, if it's at 0, the blue line is the in-plane. So at 0 degrees, i.e. normal to the surface, you have no in-plane sensitivity, but you have maximum out-of-plane sensitivity. And as you move away either side in terms of that angle of illumination, so you can see we increase the in-plane component and we decrease the out of plane component. And it's possible to mathematically separate those so that we can actually end up. So what does shearing mean? It's actually a way in the instrument of just splitting the images, and we use those split images to interfere with each other, so that you'll hear me talk about, we can do horizontal shearing, which is great for doing the horizontal component, vertical, and on round things and pressure vessels and things like that, we can actually do radial shearing, so we can look at the bulginess, we can look at everything together. To get the data out of the fringe patterns, we can add known precise movements sequentially, and that allows us to not just get the amount, but the degree, the angle, which way it's going. You know, if you remember Ordnance Survey maps, you wanted to know whether you were climbing a hill or you were going down a valley. Well, that's what we wanted to do here, so that we can then get an overall strain field on the target. And the reason we do it with shearing interferometry, and Loughborough invented a technique where we would just look for straight bending, is that here is a little rubber pressure vessel. And what we've done is we've put a little bit of bulge. And if you're looking for displacement, here you can see with conventional speckle interferometry, we get a series of concentric fringes. And if we cut a line through the middle, we can see how the object has bulged. With shearing interferometry, we get the first differential. We're measuring the rate of change of bending. And so imagine you're climbing that hill. At first, you're going up very rapidly. Then you get to a point where it starts to slow down. And then you start going down and down and down until you get to a point where it starts to go up again. So that's the first differential. Why is that important? Well, when it comes to putting a small scratch or cut into that membrane, you can see how clearly it is defined by the rate of change, whereas with the speckled, the conventional displacement fringes, you hardly notice it. But here you can see quite clearly where the damage is. And here you can see with this X, this is a 5mm thick X on the thing. Here I've doubled it in the horizontal axis, so I've put 5mm of shear, and here you can see I've doubled up again. I've put 10mm. Now, if you are clever with the way you organize the optics, this is a classic fracture mechanics specimen. So we put these in tensile test machines. This is a British standard testing for looking at the fracture mechanics ahead of a crack tip. So you grow a tiny little crack there with a fatigue type process, and here is the strain field ahead of that crack. And in fact, you also, if you remember your fracture mechanics and your von Mises and what have you, and your Tresca conditions, you actually get two lobes here, one here and one here. And we validated that against FE, and it's an absolute perfect match. So we've done a lot of work in looking at the stress intensity factors, the strain integrals. In other words, how much energy is around the crack, and where will it go? What energy will it need to propagate? So we have an ability to see the crack in all its severity. That's the sort of academic validation to what we're doing. And it's not just little things, oh, they're not little, lifeboats are quite big, but here you can see this is the elevated section around Birmingham. This is the M6. That's me up in a cherry picker looking at one of the box girder bridge beams. And these are hollow section beams. They're about 2 meters by 1 meter. And for some reason, the welder, when he made it, decided to leave a gap on one of the welds, and the Highways Authority wanted to know what happens. And if you imagine under load, the horizontal strain, if it was nice and uniform, you get like these nice vertical fringes. And if you were looking at the vertical strain component, you'd expect to see the vertical fringe, the horizontal fringes break away from the neutral axis. Here is the gap. That's the view that the instrument is seeing. And here you can see fringes nucleating in the gap. And that's bad news, because that's telling us that we've got strain nucleation, we've got a concentration. But what's really bad is we've sort of got kinky fringes here. And kinky fringes are really bad news, because what we're doing is we're able to see the incipient crack that's forming, and that wasn't visible. That was looked at with X-ray, you name it, they did it. And but what we've got here is, you can see here now, when we validated these with strain gauges, we can actually measure the whole strain field, so that we could look at the impact. So this is a 1,000 by 1,000 strain points, giving us a complete strain map in the various axes, so we can then sum those up to come up with the principal stresses, etc. So it's a way of quantified assessment of the damage. Here we're looking at, one of the interesting things is torque, to be able to actually visualize torque and see when people put inserts into structures, glued composite structures. Here, this region here, the inner and outer sleeve are bonded well together, and the rivet is only there as a safety measure, and you can see a uniform transfer of torque. Here, the bonding has failed, and the load has gone on to the rivet, and we can now see how the ability to transmit torque through that shaft or through that mast is severely compromised. So you've got a quantified way of saying this is damaged, it needs repair. And there are other things. These are machine wrapped pipes and things. And what's interesting is the instrument has this shaping piece to cope with all sorts of different geometries of structure. Defect types. Well, at manufacturing, we have the usual set of sinners of what goes on. What's interesting is that we get an additional set of in-service defects, usually as a consequence of impact. This time of the year, we start seeing condensation that can creep in, freeze, fire, fatigue, big one. A lot of people are under the misconception that composites don't suffer fatigue damage. They do. Breakages, etc. So depending upon what you're looking for, what type of assessment, you can get that. One of the things that was very interesting was when we moved, working with the RNLI, when they moved from steel hulls to composite, these are sandwich hulls, skin, foam, skin. In the first, this is the darker color is the Trent class, and the lighter mauve color is the 7 class. You can see these are the number of safety critical defects we identified. And as we were able to work with the boatyards, and the boatyards always would claim they never made a bad boat, obviously, but because the technology was relatively new, in the first instance, there were a high number of defects, and these defects will typically cost £1,500 to £2,000 a repair. So you're taking a big chunk out of your margin on a new hull. But what happened was we were able to work with them, and you can see with the boat numbers, we brought the defect count down because we were able to give actual positive feedback as to what was happening. And in terms of damage, this is a Tamar when she's nosed into something, and the boats do take a lot of damage, and I'm sure you appreciate that when they're out doing their job. But it looks pretty cosmetically horrible, but in actual fact, we were able to assess what the damage was to the hull. You can see there's some cracking on the deck, and she was repaired beautifully. So I mentioned earlier on the glove, but there's all sorts of different types of defect. If people start drilling things in an unauthorized manner, crushing problems, resin enrichment, couldn't resist that. That was put in with a router, and that's a very small thinning of a foam core so that we get resin enrichment there. But there's all sorts of different types of defect. This is one, this for example is the inside of a Tamar hull after she's had some damage. And we were able to see that there was quite a lot of damage either side of that bulkhead. And here you can see the vessel being repaired. This is a pilot boat, again, quite a large composite vessel. The engine room had a fire. The fire prevention system didn't kick in. But once everything was stripped back, we were able to assess the performance of the hull and identify that the hull was not damaged. It was just the insulation had done its job right. Rigging is another issue of challenge. So here we have a machine that you can feed the rigging through. And what we actually do is, because we're measuring the strain, if there's any damage, and we've done it with calibration rigs, if there's any damage, we can actually see the strain influence on where the damage is on that piece of rigging. And we can assign numbers so that we can say if the numbers exceed a certain degree of strain anomaly, the instrument can then alert the operator and say, do you want to make a decision at this point? Pressure vessels, wrap bottles, those sorts of things. Again, here, very tiny increase in pressure, and you can see this bottle has not lived a good life. That's usually an thin wall aluminium vessel, but then it's been wrapped with, machine wrapped with carbon. And that old myth, if you drop your crash helmet, you need to get it replaced. Well, you will be horrified to know that most of the composite crash helmets that people spend, and as a motorcyclist, I'm very conscious of my head, but these are carbon fiber helmets coming out of an automatic machine in China. There's 4 factories that make most of the carbon helmets in the world. 3 are semi-automatic, 1's automatic. These are 8 helmets taken from a sequence of the automatic machine. And can you look at the variation in performance? And what we want to see is a uniform grey. What we don't want to see is black patterns. You know, these are fatality, you know, this is just, and there is no QA in crash helmets, whether it's motorcycles, winter sport, equestrian, you name it. And we've found a lot of trouble there. Fatigue, and I'm getting, Chairman, close to the end, so you'll be pleased to know I'm going to shut up soon. When you've got a beautiful, nice piece of monolithic and you tap it, it rings like a bell. And here you can see we've just used a hairdryer or a thermal source to warm it up by a degree or so. So here you can see the horizontal in-plane strain. It's nice and uniform. After a bit of shaking on a fatigue table, the fringes are starting to get a bit raggedy. You're beginning to just see a little bit of structure in there. And when we go for a bit more, look, the fringes are really upset, and we can now see weakening of the matrix on the fibers. With UT, etc., that would look perfect. You hit it, tap it, it sounds like a dull thud, because the interfacial ability has now been severely compromised, but it's still intact. So this allows us to relife things and check things in a fatigue. So to conclude, I've tried to explain the sort of the various failure modes and introduce some of the constructional issues, tried to introduce why we have different means of configuration, what this means to residual life of components and repair strategies, how you go about it, and we can test the repair to make sure it's good enough to go back into service. I've tried to outline the difference between active and passive techniques, where people are just looking for anomalies in density of, say, an X-ray or what have you. How we can predict residual life and show that a lot of thinking about composites is sometimes compromised when people try and apply ductile thinking to what are fairly brittle structures. But most importantly, we've addressed the MABE, the Maritime Accident Investigation Board, and with BINT, we now have the ability to now start providing people with competent technicians to do the job. So with that, I will shut up.
Well, thank you, John. That's a very informative, fascinating presentation. There don't appear to be any burning questions straight away, so I suggest we go on to Peter, and we'll have a Q&A at the end of Peter's presentation. So if you're ready, Peter, over to you.
Right. I hope you can see my screen, which I've shared.
That's great.
Perfect. So thank you so much, John and John, for the introduction and a fantastic presentation. Unfortunately, my presentation is a lot boring than John's because it's more focused on the classification and the legislative side of the things rather than focusing on technical things. As I was introduced, my name is Peter. I'm a senior entity specialist with Lloyd's Register. For those of you who haven't heard of Lloyd's Register is world's first classification society. We've been around for about 270 years now. We were established in 1760 here in London. And as of now, we provide classification and different services to more than 22,000 ships over the world. Now, I'll not spend more time on this slide. If you want to find out more, you can scan the QR code, and it will take you to all the wonderful things that Lloyd's Register does. But one thing I would like to mention is that Lloyd's Register falls under a broader umbrella of Lloyd's Register Foundation, which is a charity organization. So whatever work we do is a nonprofit work, and we work to make the world a safer and a better place from our perspective. So, as I said, LR is a marine classification society. Marine classification, as defined by, or its definition is, it's an independent and unbiased entity which implements and publishes and develops the rules and regulations for quality and reliability of ships. In simpler words, we make sure that the ships which are going out to the sea are actually seaworthy and they are safe for the people and safe for the environment to do the jobs that they're meant to do. So, why am I going through all this backstory? Before I go into that, there is a bit more backstory that I'll have to explain to you further. So there exists an organization which is called IX, and it's International Association of Classification Societies, where different class societies across the world come together and decide on the bare minimum requirement for the marine assets. And they publish different documents. Some of them are mandatory requirements that all classification societies have to comply to. Others are more on recommendation side, but we'll be focusing on a document called W34. That is a unified requirement, W34, that deals with advanced non-destructive testings. And based on what John has explained to us, we can pretty much guess that shearography falls under that category. And if you're not sure, W34 itself defines what IX considers to be an advanced technology. So what that document says is that phased array, TOFT, digital radiography, or any other technique identified by the NDT specialist as advanced are advanced NDT technology. And what that document says is that whenever these technologies are used by a maritime industry, they have to be validated by the class society. So if it is a normal conventional ultrasonic radiography, nobody needs to validate all those things. But if it is an advanced technology which is not established, then a class society has to get involved and take certain steps to validate that advanced technology. Now, different class societies have different ways of dealing with the compliance with the W34, because W34 lists out, as I said, the bare minimum and the basic requirements that all class societies have to comply with. Based on their experience and expertise, class societies come up with their own way or own method or scheme to comply with the unified requirements. For Lloyd's, that document is known as MQPS, that is Materials and Qualification Procedures for Ship. Basically, this particular document, which is Book N, Now, there are different procedures within this document, but one of the procedures that is 17-3 that deals with the validation of advanced entity methods. If you want to have a look at this document, you can again scan the QR code and it will take you that document. It is free to download and you can go through it if you have any you can say curiosity on what the document says. Now, this document lays out pretty straightforward and clear requirements from LR that what a client or NDT service supplier needs to do to prove to the class society that their advanced method works at least as good as the conventional technology, if not better. Now, it may seem very simple auditing sort of a thing, but I would think that Simon and John would agree that if you're first in the line to get your method validated, it's not an easy thing to go through. It takes a lot of time and a lot of effort to get it validated. The first step of this validation process is that the client or the ADT supplier has to come up with a detailed proposal for their validation, which includes what type of material they're dealing with, what would be the accuracy, the repeatability, and other technical factors which are associated with that NDT technique. Then there would be a documentation audit sort of a stage where the class society will verify starting from smaller things like equipment calibration to personnel qualification to management sort of checks that whether they have a proper ISO system in place, how do they deal with client complaints, what are their corrective preventive procedures, dealing with all these client feedbacks and other things. After those things are done to the satisfaction, then there will be a physical demonstration stage. Now, for this physical demonstration, with the agreement of LR and the people applying for the validation, they will have to come up with a number of samples representing the validation that they're seeking. Now, these samples will include either, you can say, different types of reflectors or different types of defect. They can be machined defects or they can be naturally occurring defects. We would prefer to see naturally occurring defect, but sometimes it's not possible or it's not feasible financially to do those things. So we can accept either of those. And then the supplier, to validate the NDT technique, the NDT supplier will demonstrate that with using their technique, they can not only identify, but size those defects at least as good as their conventional counterparts. Now, it has to be done in two stages. That first, they will use the advanced NDT technique, that is the shearography, to scan the components. And they can use any other conventional techniques that is starting from ultrasonic testing to radiography to even destructive testing. They can even do macro sectioning of the components and have comparison of those results. And if those results are comparable, then we can say that the advanced NDT technique, that is the shearography, works as we expect it to work. And at the end of this process, they will be issued a certificate that is a validation certificate for their technique. Now, as I said, the main purpose of all this process is to comply with the requirements set forth by IX. Now, IX, since it's an association of all the classification societies, we're ensuring that everyone is on the same page. Now, different class societies may have different approaches, slightly different approaches. Some may just say that, okay, whatever requirements put forth by IX, we'll just comply with that. At Lloyd's, we go above and beyond that. Our requirements are much more stringent. I think John and Simon can, well, they have loads of complaints about that, oh, you require all these things, why do we need that? But we need to have a standardized process so that whoever is doing this process across the world is doing it in a safe procedure so that the NDT is not dependent on an individual, but rather than a process. So we're focusing on the process of, you can say, the NDT so that we get reliable results every time to enhance safety and structural integrity of the component under inspection. And the main purpose of this exercise is building confidence in the advanced NDT technique, because we have enough statistical data to prove the reliability and repeatability of the conventional techniques. We need to do the same thing for the advanced technique, that is the shearography. That is why we go through all this pain of coming up with the samples, scanning them, even maybe destroying some of them to do the macro-sectioning of those samples and comparing them with the results from shearography. Now, the document you can see on the right is the Unified Requirement W34. That is also free to download from the IX website. If you want, you can just do a simple Google search and you can find this document very easily. Now, that's pretty much it from my side. From the classification society point of view, that you have to build the confidence and you have to prove that the system works at least as good as the conventional counterpart. Now, you would ask the question that why do we need to go through all these, painful processes of establishing all this confidence and all these things? Because I think John and Simon both have published enough technical papers that they've been doing it for a longer period of time. So they would say that, no, we have already proven it through our technical publications and all these other things. So I would always close with this single beautiful photograph. The ship, the aircraft carrier you can see in the back is the USS George H.W. Bush, which is a nuclear-powered aircraft carrier. And the smaller ship you can see in front of it is ITS Amerigo Vespucci. Now, the interesting thing about this photograph is that these ships are built not even 100 years apart. So the technology has gone from a wind-powered, sail-powered ship to a nuclear aircraft carrier in a time of less than 100 period, which gives us an idea that how fast the technology evolves and gets accepted by the industry. So as a glass society, we make sure through this process that whatever we're doing it on solid basis, and we have enough confidence in the system and the new technology that we're adopting in the maritime industry, so that we ensure the safety of life at sea, so that the human beings and the environment are protected when the asset goes out into the sea. And again, that brings to the end of my boring legislative presentation. And if you have any questions related to this thing, please feel free to get in touch. And thank you so much for the presentation, the opportunity to present here. I will stop sharing my screen.
Great. Well, thank you, Peter. I'm actually extremely encouraged to see Lloyd's Register their active involvement in how to certify and approve of this technology. I think in the innovation space, we often feel that the regulators, be they flag states or class societies, sometimes are a little bit behind the technology, and we struggle to get technology adopted because of those reasons. So I think a thorough but timely approach to regulatory approval is extremely encouraging. So thank you for that, and I very much welcome it.
Well, we're currently in the process of the validation for shearography with Simon and John. And we've gone through about 65–70% of the process. And during this validation process, we have made sure that we involve all the relevant or people who are interested in this thing. So NAIB is involved. I think some other inspection agencies and classification and legislative bodies will be involved in the process. So hopefully we'll get it done. It's a slow moving, it's a painful process, especially for the people doing it. But it's a necessary process that we have to go through.
Absolutely. Very good. Right. Well, we've got a question from Simran Khanna. Thanks for the presentation, John and Peter. I want to clarify the difference between ESPI and LSI, and in what cases would you use one or the other? I'm not entirely sure who that's aimed at. Is that you, John?
Yeah.
Right. ESPI was something I cut my teeth on. I was there when it was sort of being invented. We used to use holographic interferometry, and that measures displacement. So if you, looking at your desk now, if you move your coffee cup around on your desk from one place to another, the ESPI would produce a set of contour fringes of displacement that would show how the table has bent as a function of moving the coffee cup. That doesn't really tell us how things break. And in NDT, that's what we're really interested in. And that example of the sphere, the inflatable rubber sphere, showed that when we put the scratch or the cut into it, ESPI doesn't really resolve that. You can try and numerically differentiate the data, but that's highly error prone. And trust me, I know, I was there. So we developed the optical differentiator, which is the shearing interferometry, so that we could measure the rate of change of that. And by moving to the different axes, the in-plane and out-of-plane axes, with respect to composites, it allows us to really nail what's going on in the structure, which you can't do with an out-of-plane system, and you certainly can't do with ESPI. I know, I've built multiple systems that have been all around the world on these things, and it doesn't work very well. You need to have these derivative type techniques, which give you an ability to classify, and that's what we're trying to impress Peter's organization with, that it actually provides the surveyor with some meaningful data that allows assessment to be done in a quantified fashion.
Great, thank you.
Does that answer your question adequately?
We'll wait for... Oh,
okay. All right. Thanks, Simran.
Great. So I was very interested by the rubber glove left in the laminate. It reminded me of when I was working in the shipyard building tankers, how we managed to spray paint a sandwich onto a stringer. And really discovered it when we did the tank inspection at the end of the day. So yes, these things are very real. And whilst we're waiting for some more questions, if I could ask John, I understand this to be a sort of surface technology, i.e. you examining the surface of the composite. And therefore, I'm interested in what sort of thickness of material and what depth of defect we might be able to discover, and whether you need access to both sides of the material.
Right. Excellent questions. And the usual ones. Most of the techniques are single-sided, ultrasonic, they're all. What we're doing is we're putting the entire structure under some representative work. So the vacuum chuck, that thing that you saw Andy using on the lifeboats, it's got a little rubber seal around it. It's got 3 feet equipositioned, sucks itself onto the hull with a little low pressure, and then it just pulls the hull against the 3 feet. And the way we've designed the structure is incredibly stiff. So what it does is it deforms the entire structure. It's putting the whole structure under load. So in terms of on the lifeboats, we're typically looking at a 5mm external skin, say a carbon skin. We're looking at 4 25mm rigid PVC foam blocks bonded together, so that way it allows them to shape the foam inside the hull when they're putting them in. So in effect, we've got 100mm of foam in there, and then we've got another few millimeters up to 5mm skin on the other side. And we can look at and see the defects when, if there's foam that's butting up to itself and it hasn't been buttered up, enough with adhesive, so there's a gap there. We can see those things. We can see, and that's from the outside of the hull. We can look at that whole 110mm thick structure, which is not, an inconsiderable thing. Monolithic composites. The thickest we've gone to is for naval structures, where we've been up to structures that were 160 millimeters thick in monolithic carbon. That requires a bit of effort because they're bloody strong. Sorry, rather strong. That's an engineering term. I apologize. The depth, we're really, one of the things we're doing, I'm sorry, my study clock is going off there. What we're able to do is assess the influence of the defect in the structure. So a popular misconception is porosity. We often have people saying, oh, can you spot porosity? Well, one of the ways of blunting a crack is usually you drill a hole at the front so that you put a nice smooth curved thing in. And foam is full of porosity. That's how it works. But if the porosity is causing weakness to the structure, then we will see that because we will be able to measure it. But quite often, and this is where, when you get into comparative studies, we get these round robin things where people they usually stick pieces of aluminium foil in. I don't know why, but it's always aluminium foil. They'll put some porosity in, and then they'll drill a hole at the back, and they'll say, can you find these things? Because the hole in the back, they say, is delamination. And no, it's not. It's a hole in the back.
Yeah.
And you've weakened the structure. Big deal. That is not delamination, because the way you drill, quite often we even have some numpties that use twist drills, and they really delaminate the structure as it drills in. Aluminium bonds, surprisingly, ends up sticking in. So sometimes you can find things become part of the structure. And going to the porosity question, if there is a lot of porosity in a region where you don't want it, and it's bigger than the shear strength of the material can withstand, then yes, you'll see a weakening in the structure. But it's quite amusing when people send me structures and say, we sent you a test piece, it had 3 defects in it. And I say, well, which of the 9 defects are your 3? And they said, yeah, but you missed the porosity. And I go, but that wasn't a problem. It's a cosmetic, and this is the difference between brittle and ductile structures. It's how did the porosity get there, for example. I've never seen a crack initiate from a small hollow sphere.
Yeah.
I've seen it blunted, but
we've had that debate in metallic materials about how serious is deeply buried porosity. But anyway, and I would encourage people for the last couple of minutes, if there are any questions, just to jot them down. Just one more while I'm waiting for that, John. Just take us through how you load the structure. And you talk about vacuum, so you pull.
Right, there are many. So I originated, my original sort of studies were in engine design, both automotive and aerospace. So there I was using vibration. So if there is any damage or mass loading that's not expected, what you would see is the mode shapes, the resonant mode shapes. They would be heavily influenced by these things. So internal features. So if you're looking for a vibration type problem on blades, and resonance is a big issue. So everyone knows about the pure modal families, but God has got a great sense of humor. And what he does is he plays and he says, oh, I'll take 20% of that mode, and I'll take 40% of that mode, and I'll take some of that, and I'll make a brand new mode that looks really pretty. And it sits right in the middle of the running range of the engine. And unless you check for the full scan, so we would do full modal analysis. So that's one type of inspection. Heat is great because it's ever so simple. I mean, I have a little cheap hairdryer, And I have fixed many, many tens of millions of pounds worth of structures just by wafting it with a hairdryer, letting the structure expand, and that shows all the internal structure and damage. We can quantify that properly with infrared lamps and put known amount of energies in and get known responses and all of that. Pressure and vacuum, so you can either pressurize something or put a very light vacuum in, so tubes, pipes, pressure vessels, etc., junctions, flanges, that they do very well with that. Mechanical loading, where we physically either pull or push or twist or what have you. And a lot of things in the maritime sector, people tend to put things on tensile test machines and pull them. Mm. Well, I've never seen a ship or a boat that sort of suffers front and backy type stuff. I see twisty stuff, you know, so torsion is usually, and the response of a structure, particularly repairs, scarf angles and things like that, when you start repairing these things, critical, because under tension, they pass dead easy. Start putting a twist on and they pop out like blackheads, you know, the repairs. So there's all sorts of things: pressure, heat, mechanical loading, etc., vibration. It really depends what the type of problem is.
Very good.
And now Rob has asked a question. Are there any defect types that you think laser shearography cannot reliably detect? If I'm honest, if there's a defect in the target, in the component, and it's causing damage, it will weaken the structure. So we usually find them unless they are embedded so deeply that they don't actually influence the way we've loaded them, in which case it's our failure of the loading mechanism. One of the things I'm doing a lot of work on at the moment is concrete structures. You've heard of these, you know, these various aerated concrete, but also looking at concrete as a composite structure. It's a compressive structure with steel componentry in it. And one of the techniques we've been using to get deep into the concrete, rather than trying to go with infrared heating from the outside, is we've used inductive heating of the rebar, so that we could actually get the heat into the structure at deep levels, because it's usually the rebar concrete interface that's quite a high level problem. And yeah.
Thank you. I see, apologies, Rob, I missed your questions. I'm afraid to say that we've run out of time. So I'm going to ask that, would it be possible for John to respond to those two questions?
Yes.
We put them on the MarRI website. So it remains for me to thank John and Peter for extremely informative presentations on what is a fascinating and, you know, got real potential in terms of marine structures, technology for structural integrity. I'd also like to thank Wenjuan and Orla for setting this conference up. This will be available on our website, and apologies that I didn't get those last couple of questions, but if you do have any questions, I'm sure our presenters would be happy to answer them. Thank you all, and have a good day. Goodbye.
Thank you so much.
Thank you, John.
Thank you.